Hello friends, welcome back to the third week of our course on the topic of principles of mechanical measurements, and this week we are going to talk about a very interesting topic, that is digital techniques in measurement. You all know that nowadays everything is moving towards digitalization or digitization. Both terms are used interchangeably, so we shall also be using both of them. Now, while earlier approach for most of the experimental works was to use some kind of analog instruments, analog means where directly we are getting the value in terms of either movement of an indicator over a dial or by movement of a fluid through a capillary tube or something similar, thereby directly giving us the value, or rather we have to read the value from some scale which is inscribed on the device itself. Nowadays all kind of measurement device and everything else is moving towards digital media, where we are getting the numbers directly from the screen, and we do not have to deal with some continuous movement of certain indicator or something similar. Rather, we are just interested with the final number that we are getting. You can compare this to our modern day life, like some earlier days, those movies used to be, movies or music etc., used to be coming in the record players, which are something like an analog media, and later on, or the cassettes. Maybe some of you may have seen the cassettes, tape recorders, but it is unlikely that or it is very likely that many of you have not seen at all. Now everyone moved to CD players and later on the USB sticks, where we are actually storing the entire content of a movie or a large quantity of music or maybe several movies into just a very small USB stick, which may be of the shape of just a finger or even fingernail, I should say, or even smaller than that sometimes. Like the memory cards that you use in cameras or in media in mobile phones, they are extremely small in size, and that power of miniaturization has been brought in by this era of digitization. And therefore, it is very important that before we start talking about different measuring tools itself, we have to talk a bit about the digital techniques that we commonly use in the field of measurements. The way how we convert common analog signals to digitals, and how we recover the digital data back to the analog form, and also several relevant topics associated with that. That will be our focus of discussion in this particular week. We now know from our discussion from the previous week is that any measurement system can be viewed to be some kind of mathematical operator, something which is known as the transfer function, which takes one input, sometimes even multiple inputs, by making an interface between the device and the physical media or physical system, and that single input or multiple inputs goes through some kind of mathematical operation, leading to the production of one or more number of outputs. In the previous chapter, we restricted ourselves to single input single output devices, because it is not possible to deal with more inputs or outputs simultaneously in a course. Rather, that will become more like a research topic. So, and here also we are going restricting ourselves to a single input single output kind of situation. Now we know that whatever input we provide, depending upon the transfer function associated with the measurement system, we get a corresponding output. Let us take an example. Let us just think about a first order system, and we know that the transfer function for a first order is given like this form: k upon tau d plus 1. You already have seen the development of this equation, and I am sure you have already used this one for solving some problems. Now let us see the xt, which is a time dependent input signal. Let us assume that our input is a sinusoidal function of this form, and our system, the first order system, is having its static gain to be equal to 1 and also a time constant of 0.001 second. Now we are supplying a periodic input to this, and that corresponding periodic signal can be viewed to be a combination of two harmonics, first one having omega equal to 2, second one is having omega equal to 20, and also the corresponding amplitudes. First one is having an amplitude of 1 and second one is of 0.3. I hope you remember we solved an example problem there, mostly to show the effect of tau on the form of the periodic outputs. It is precisely that problem. So, I am directly taking the solution from that. You know how to develop the solution, where in the solution side also we are having extremely small time delays. So, 0.23 degree of time delay has been, or I should say phase delay has been introduced in the first harmonics, and 2.3 degree has been introduced in the second one, and their amplitude remains the same. So, this static gain and time constant, particularly the time constant, corresponds to excellent frequency response, both phase and amplitude point of view. We are also familiar with their phase form from the example that we solved last week. This is the input side and this is the corresponding output side. Output is following the input quite in a fine manner. Now, our objective here is not to focus on the shape of the output, because that is what we have discussed. We now know that depending upon the magnitude of this tau, we can have different shapes. But once we have this particular shape, this continuous representation of the output is what we refer as the analog output. Corresponding to this particular analog signal that we are getting from the physical system, our system is receiving the analog signal, and also whatever mathematical operation it is doing, following that it is giving the output also as a analog signal like this, where we have the value of y available at every possible time instant over the entire span of the experiment, and also theoretically it is possible to have therefore infinite number of data points, that for any value of t we have a corresponding value of y, and hence any other once we know this particular mathematical form, then any other operation that we want to do on this, at least theoretically we can definitely do that. So, analog signal provides several advantages. The first one is it is the most obvious one, it is the natural signal itself, and so it is a highly accurate representation of what we are trying to get. Now, we have a very high density of information, because theoretically we have infinite number of data points, and we can extract the value of the output signal y at any possible time span starting from t equal to 0 to t equal to 4 in this example. For any value of t we have some y value available. Then there is no quantization error. What is quantization? We shall be coming very shortly. Less bandwidth requirement, and also there is no pre-processing requirement for such kind of instruments or such kind of signals rather. We are giving the input signal in its raw form like this one, and whatever output we are getting, we take that in its raw form itself. We do not have to go for any kind of pre-processing of the input, and also in most cases we do not need any kind of post-processing for the output as well. However, despite having such advantages, the analog signal has some disadvantages of its own as well. The first one, and a very big issue, analog signals are generally susceptible to noise, leading to the distortion and loss of signal. Noise means say whenever you are doing some experiment, the noise refers to what you want to measure. Apart from that, certain other parameters are also influencing your output. Say for example, you are using a manometer to measure the pressure. You are using a mercury manometer, and because of the pressure difference between the atmosphere and the physical system that you are handling, because of their pressure difference, there is a deflection in the mercury column, and by measuring the height difference between the mercury column in the two arms of the U-tube manometer, we can get the idea about the pressure in the physical system. However, the height of the mercury column in a manometer can also be influenced by if there is a large change in temperature across the two arms, or maybe in the local location, like whatever value of deflection in mercury column you are getting for a certain temperature, if the temperature of the surrounding increases by significant amount, mercury may suffer some amount of thermal expansion, leading to a different value of the deflection. Also, if there is some kind of vibration available in the, if there is a vibration of the floor where you are doing the experiment, that may get reflected. Another big issue may be there. Suppose this is your mercury column, this is the U, and your rather this is a U-tube manometer, and this is your mercury column, this is the height difference that we are talking about. Now, suppose this particular manometer is mounted on some vehicle. As long as the vehicle is moving with a constant velocity, or it is stationary, then there is no issue. But if this if this vehicle starts to accelerate, then what will happen? Your mercury manometer will be tilted like this, leading to a different amount of deflection maybe of the mercury column in this, if the vehicle is tilted. Or suppose our vehicle is not tilted, but or mercury, I should say the manometer is not tilted, but the vehicle is accelerating. Now, because of the acceleration, it may happen that the mercury column, instead of being horizontal, that appears in some sort of angle. Now there is a big issue how to get the measurement, like whether should we take this particular value, or should we take this particular value, or should we take mean, then exactly which one refers to the central line, there is lots of confusion to deal with. So, the analog signal is susceptible to noise coming from generally from the surroundings, and also sometimes maybe from the physical system itself. There is editing limitations. Once some portion of the signal is lost, it is not possible to recover that. Infinite data, which is an advantage, but that leads to very expensive storage, because when we are dealing with this kind of output data, it always looks good to see this kind of signal on a cathode ray oscilloscope kind of device, but when we are talking about saving this, then we theoretically have to save infinite number of data, leading to extreme difficulty in storing and also extreme difficulty in post processing the same amount of data. Then generation and transmission loss, particularly transmitting this kind of medium over a long distance will always lead to some loss in this. Just think about the normal power supply. Generally, we get power supplied to our houses in the form through the high tension lines in the form of 440 volt 50 hertz signal. But if that same wire is supplying power over say 100 kilometer, then because of the joule heating and other kind of induction losses, a significant amount of voltage drop you may experience at the consumer's end. That is what we refer as this transmission loss. The power requirement can also be quite high, particularly the hardware are quite costly. So, analog signals have certain issues on its own. There is another problem, sometimes if we are dealing with an instrument which is having a dial gauge, like this is a dial and we have an indicator moving over the dial gauge, like in several common electrical devices like voltmeter and ammeter, like in pressure dial gauges, sometimes in certain temperature measuring instruments, tachometer, which is generally used for measuring RPM, all have this kind of device. And most often you will find that the scale that we have on the device are not linear, rather the values are quite cramped up towards the initial part and then gradually getting relaxed as we are moving towards much higher values. So, linearity is not maintained, and reading values with a high precision within this zone can be very difficult. So, analog instruments have problems there of their own, while their best advantage is the absence of quantization error, I should say absence of the quantization error, and very accurate representation, and also the absence or non-requirement of any kind of pre-processing. Their biggest problem is the susceptibility to noise, to other external forcing systems, very large storage requirement, and also the transmission losses, plus the hardware are always very costly. Just just think about, say you have one book, a book of 500 pages, and the material of that book is also available in the form of an e-book, which is generally coming in a PDF as a PDF file. Now compare their sizes, where your digital item can be stored anywhere. You can store it in your computer, you can store it in some external hard disk, you can also store it in a very small say memory card kind of thing, but that book requires a specific storage. It also needs to be handled very precisely, because any mishandling may lead to damage of the book, maybe some page may get damaged, may have permanent damage, making it impossible to read. But there is no such problem with that e-book, and also you can make any number of copies of that e-book if allowed, and so you can carry it with it anywhere you go, which is not possible with the book itself. That is the biggest advantage of having a digital media over an analog one. So, because of all these problems, particularly with storing and handling and transmitting the analog media, and also the susceptibility to the surrounding conditions, the whole world is moving to the digital platform. And let us just summarize the advantages that we may get with digital signal and corresponding processing. Firstly, greater immunity towards noise. We shall be shortly seeing one example. Digital signals are, you can say, they are totally immune to the surrounding effects, thereby whatever input you are giving, that comes out exactly in the same form or whatever form we want that. That enables simultaneous multi-directional transmission without any kind of transmission losses. Hardly any loss over long distance transmission, as I just mentioned. Secure and easy to handle. You can easily record, store, or store the data. Like think about recording a song in a CD or in an USB stick. That is much easier than recording in a taped medium or storing in a taped medium. The display and post processing parts are also quite easier. You can, once the data is available with you, you can save it in any place, and then you can use any suitable software to do the editing. Like suppose if you want to edit, say for a certain situation, you have the marks of students in a particular class are available, and you have stored that marks in a file in your computer. Then anytime you can go back to the file, and whatever kind of post processing you want to do on that, you can do it using a suitable software. And that same applies to any other kind of digital media. Less storage requirement, in fact almost negligible amount of storage requirement compared to the analog one. We have already given example of that book. Ease of editing, possible to recover damaged signal as well. We shall be seeing one example also. Programmability and multitasking or multiplexing means the same digital media can be used for different kinds of purposes, and they can also be used simultaneously. Then repeatability or reproducibility, very easily we can make copies of that, or we can reproduce the same thing into another device. Hardwares are also commonly cheap, we can easily upgrade that, and also the hardwares are generally suitable for mass production. Like think about a small chip. Now it is much easier to go for mass production of a small chip compared to a large taped kind of storage media. And finally, the insensitivity to the external factors like temperature, dust, vibration, hardly any aging effect you will see, but these factors are always very much influential on the analog signals. So the digital signal comes with so many of advantages, but there are certain issues as well. One is the quantization error, which was not present, or which is not present with the analog signal. Quantization leads to the loss of information. What we mean by quantization, I shall be coming to the next slide. Finite word length issue leading to truncation error, again I shall be discussing about this later on. Bandwidth requirement generally is a bit larger for the digital media. They are difficult to synchronize. Synchronization refers to, suppose you want to record one live incident going on. Now there are two things that you have to record. One is of course the movement or whatever is going on in form of light, and that is the scene itself, and other is the corresponding sound. And now you are recording them generally in using two different kinds of instruments and converting both of them to corresponding digital form. Then you need to synchronize that properly, otherwise what will happen, you must have experience of seeing a very badly synchronized movie where the sound comes maybe after 10 seconds after the actual speaker has already spoken. So it is very irritating to face with such kind of situation, but that synchronization is a bit difficult and requires proper expertise, which generally is not at all required in an analog media. And greater attenuation leading to reduction in the signal strength. But despite such disadvantages, there are ways we can overcome disadvantages, and the weight of the advantages are much more compared to disadvantages, forcing the world or inventors to move towards the digital side. Effort is on, or there are standard practices of tackling these disadvantages, means how to reduce the quantization error, how to have better synchronization or less attenuation of the stored media or transmitted media. There are quite standard procedure, and newer methods are coming up every day. So hopefully these errors also will not be that much significant in times to come. So let us now the some examples that we are talking about. On the left hand side, suppose you want to paint your house or one particular wall of your bedroom, and the corresponding supplier supplies you or provides you with a color bar chart. Now two kinds of bar chart he has given to you. In one, the one on the left, that is my left, that is what I am talking about. This one here, you are having so many shades of color, but suppose if you want to pick up any one of them, then it is it will be very difficult for you to explain that. Like suppose you have decided on this color. Now without the help of the card itself, how can you make the painter understand about your choice? It will be very difficult, it will be very painstaking. Look at how many shades of pink you have. Like suppose you have decided to take this particular one, but how you will make it understand? Because all these arounds are having more or less similar shade, they all can be categorized as pink, and so you have to take this card and physically you have to show. But then after you have selected this and you want to tell your friend about your choice of color, then again you are in a soup, because you do not know the name of this one, or rather only idea that you can give is it is a pink, light or dark or something, but there are so many surrounding shades which are also satisfying the same criterion. Now look at what we have here. Here each color has been given certain number, and therefore if you want to select any one of them, then you can easily refer by number. Like suppose you have selected this particular one, then you do not need to at all talk about whether it is pink or green, light or dark, rather you can always say that I have selected color number 71, and this way if this particular chart is a standard one, then without taking the physical chart physically with you, you can tell the painter that you have chosen 71. You can go to the shop and purchase paint number 71. You can also inform anyone interested about what is your choice. So that is what is digitization, or the advantage of going for digitization, where everything is represented in terms of numbers. We are not depending upon our senses to get a proper idea or overall idea about our selection, rather we are giving a number, assigning a number to everything else, and in terms of number itself we are giving all possible characteristics. Like you must have heard about this kind of format RGB. RGB refers to red, green, blue. This is one of the standard color format used by computers, where every color can be categorized as in either RGB, or depending upon how much percentage of red, how much percentage of green and how much percentage of blue has been selected or has been combined to get that final color. Using that we can give numbers to any color or any arbitrary color. There is quite common another standard CMYK, or sometimes just CMY, which refers to cyan, magenta and yellow. Here again the colors are cyan, magenta and yellow, and generally black associated with that. So again combining these three and sometimes black, we can develop any shades of color, and taking into account the fraction of C, fraction of M and fraction of Y, we can give some name to that. So this way something like color, which generally is not considered as a proper technical quantity, we can also give them a technical look, which is not possible in the analog framework, but is very much possible in the digital framework. So the method of digitization, we know that, I am sure all of you have some idea about what we refer by digitization. We also briefly referred to this in the first week itself. This one is our analog signal. For the purpose of digitization, instead of plotting or measuring or rather getting such continuous representation of the out signal, we get the value of the signal only at certain time interval. Say at this particular time instant we have taken the measurement and this value is coming out to be this, then at this particular instant we have measured the value to be like this, then at this instant we have measured the value as this instant we have measured the value to be this, and this continuing this way, this is the final instant where we are getting the value to be this. So once you have done that, you are available or you are ending up with a table where time is one side and the value of y at that particular time instant is on the other side, and you can store this table in whatever format you want, and then you can use any kind of software to produce a graph corresponding to this. Of course, the value of t or the choice of t definitely matters. Like in this case, you can see that we are taking any successive measurement of after this particular time instant apart, this delta t, or sometimes commonly referred as h. So, after every delta t apart or this h apart, we are getting the measurement. Delta t remains constant, but the value of delta t itself is very important, the value of this h. If the value of delta t is too large, then we may end up with very few number of data. Like suppose if your choice of delta t is large, you may have one value somewhere here, then one here, then another one here, another one here, and finally one here. Now, it will be very difficult to plot the curve using this, because you do not know the do not have all the interior details. So, your curve may look something like this, which is completely ignoring this particular curve part of the curve, and also primarily giving a quite wrong representation. Look at this particular case here. If we use the selected values of delta t, we are getting a quite nice representation of the curve, because it is able to capture these peaks also, it is also able to capture these troughs, and we are going to get a decent representation. But we can make it even better if we choose an even smaller delta t. Just check out the delta t in this particular case. Here our delta t is much smaller, actually half of the previous case, leading to the development of a double number of data points. So, we are having a much rich data set in terms of y versus t here, and it is expected that we are going to get a much better representation if we use this data to reproduce the original curve. Let us see another example, another workout example. So, this is the data set that we had originally, which is the analog output. Now, with an h value of 0.5 second, here the total span is of 4 second. So, with a time span of time gap of 0.5 second, we have measured the values, and you can see here you are getting the first one at t equal to 0, and then after every 0.5 second apart, we are getting the measurement, leading to a total of 9 number of data points. We are having 9 data sets, one corresponding to t equal to 0, and then 8 more 0.5 second apart subsequently. And if we now plot these 9 data points and join them by the suitable line, then we are most likely to end up with a curve something like this. Is it looking similar to the original analog input or output? Not at all, it is looking completely different. So, let us make h smaller so that we can have more number of data points. We are taking h equal to 0.2 second, and so how many total number of data points that we are going to have with? In this case, for every time second, every 1 second apart, we are getting, for every gap of 1 second, we are getting 2 data points, where you are going to have 5. So, total number of data points you are going to have is equal to 21, one corresponding to t equal to 0, and then 5 more corresponding to each of 1 second added. And you can see this does not look does not look bad, rather it is a much more improved one, and if we plot, it may be looking somewhat like this. Which is definitely much more closer compared to the earlier one. So, this is definitely wrong, but this is not that bad, but still it is missing certain useful information from the original output. We can easily compare this one with the original analog signal, and we can see despite having almost 2.5 times more number, or sorry, double number of data points, more than double number of data points, we are yet to reach the final precise step. So, we increase it further, we have chosen h equal to 0.05 second. That means, for every second we are having 20 number of data points, and leading to a total of, we are having a total span of 40 seconds. So, 20 total span of 4 seconds, so 20 into 4 is 80 plus 1, we are having total 81 data points. And look at this, it is definitely a very good representation of the original signal. Like if we plot, it will, if we join these data points, it will be something like this. Definitely we are getting a quite good representation. Here I have joined only the points appearing in initial part, but the first point where it is crossing this or adopting negative value, that is also being quite accurately predicted, which probably was not there in the previous two cases. and it is definitely looking a much better representation. So, as the age becomes smaller, more and more number of data points comes into play, we reach a much better position. Rather, our, I should say that the digital output or digital signal keeps on approaching the analog signal. This age or corresponding the inverse of that is sometimes referred as a sampling frequency. So, in the first case your sampling frequency is just 2, because you are having only 2, or a common way of representing this one is 2 samples per second, or 2 capital S per S. In the second case we are having a sampling frequency of 5 sample per second. In this case our sample frequency is 20 samples per second. So, as the sampling frequency keeps on increasing, we are approaching a much better scenario, but of course, how many number of data points that you are going to deal with depends on how much accuracy you want. Like, we may not be needing so many data points, like you can clearly see in this case definitely you are getting much more accurate results, but we have to handle 4 times more number of data points compared to the previous case, and that is why we need much larger storage for this. So, such accuracy may not at all be required for the application which is of our concern, and hence our choice of the sampling speed or choice of the number of data points that we can deal with, that depends on the application also. But the principle of digitization remains the same. Here, instead of having a continuous measurement, we are measuring the data only at certain time intervals. This is one an advantage for digital signal over analog. In the analog signal you can see there are certain noise appearing, one here, another one here, and accordingly our signal you can see there is a distortion in this point and in this point, but compare that with the digital signal, it is also being experiencing significant amount of noise, but as the data has been digitized, or instead of dealing with a continuous representation like this, we have converted this to a set of numbers, so that hardly gets influenced by the surrounding, and we get exactly the same representation or the correct representation on the output side. Another advantage, this is an analog signal which we are amplifying, and because of the amplification it is losing its power or the energy level, and once some part of the signal has been damaged, it will be very difficult to recover that, practically impossible to recover the damaged part. But for the digital part you can see there is some distortion, but very quickly we can regenerate using the original data set and we get a correct representation, which is not possible with the analog one. So, these are just two advantages of the digital signal which we have already discussed. So, the idea of digitization is, instead of dealing with a continuous representation of the signal, we convert that to a set of data, a t versus y kind of representation, where we shall be having the magnitude of the measurement under consideration available with us after a particular time instant apart over the span of our interest, and then once we have the data set with us, we can deal with it in whatever way we want. So, just some very basic about the digital building block of our computers or any such digital instruments. Probably you are familiar with these names. The smallest building block is called a bit. One bit can store only one digit. One bit can store a single digit. When we combine 4 bits together, we call them nibble, and 8 bits together is called a byte. So, a byte refers to 8 bits together. Commonly one number is one byte is used to store one full number, where one bit can store a single digit of a number. One byte, which comprises of 8 bit, it can store one full number. Of course, depending upon the value of the number, of course will depend upon what kind of number system we are following, because the number must has to be represented by 8 digits. If the number of digits are more, then one byte alone is not sufficient. We have to go for double precision or 2 bytes or even more kind of representation. Word refers to any small functional element of digital circuitry or digital components, like here shown. Word can be combination of 2 bytes, it can also be combination of 4 bytes, commonly referred as long words, or we can have all these 8 bytes coupled together to form a very long word. If you think about, this is more an 8 bit kind of representation, a byte, So, here we have 16 bit, this is 32 bit and this is 64 bit. Like you probably have heard earlier days, the digital instruments, computers, etc. used to be in 16 bit, then converted to 32 bit, and now most of them are coming in 64 bit. The 64 bit refers to precisely this, where we have a very long word which comprises of 64 bits. Even larger units can also be formed by adding suitable prefixes, like 1 byte refers to a single character of data, just one number, as I have mentioned, which has 8 bits. And now when we have 1024 bytes combined, we call it a kilobyte. Now one question may be coming to your mind, commonly 1 k refers to 1000, like 1 kg refers to 1000 gram, 1 kilometer refers to 1000 meter. Then instead of 1000, why you are having 1024? This 1024 comes from 2 to the power 10. This 2 to the power 10 is 1024. Why 2 to the power 10? I shall be coming shortly. So, instead of using 1000, this 1024, which is reasonably close to 1000 or 2 to the power 10, is used as a conversion unit for while giving this prefix k, m, g, etc. So, 1 megabyte will be equal to 1024 kilobyte or 2 to the power 10 number of kilobyte. This way 1 gigabyte is equal to 2 to the power 10 number of megabyte, and it continues this way. Instead of using 1000 megabyte, 1 GB refers to 2 to the power 10 megabyte. So, 1 kilobyte typically corresponds to a page of plain text. 1 megabyte, it can be 4 books or 200 pages of text, or can refer to some other media also. 1 gigabyte is quite large, it is about a whole library or even bigger. It can store that much amount of books. Yes. 1 terabyte refers to several millions, 4.5 to 6 millions of books can easily be corresponding to. So, that can be all the libraries of the world combined with each other together. Then we can move to petabyte, exabyte, or even zettabyte amount of units. So, this way we can form different units, and all of them therefore refers to how much storage you are providing to store all these digital elements or the digital numbers. Now, we are talking about numbers, because in digitization we are converting a continuous signal into numbers. So, let us quickly go through numbers and their properties. We know about natural numbers and 0. Natural number refers to 1 to up to 9, and there is 0. There can be whole numbers or negative numbers. We can have integers. Integers refers to there is no fractional part, it is just the number alone, maybe with a symbol, like here this -3 has a symbol of its own. The other part can be fraction. Most of the common number can be represented as a fraction as well, and therefore, it is one important term here. This is a denominator has to be a non-zero quantity for it to be a proper fraction. Both integers and fractions are called rational numbers. The term rational numbers commonly refer to any number which can be represented by ratio like this. Like suppose if you are talking about 0.83, we can always write this as 83 upon 100, or suppose you are talking about 0.4, we can always write this as 2 by 5. So, the fractional any decimal point based numbers can always be converted to a suitable fraction, and therefore, they are all rational numbers, and integers are also definitely rational numbers. But it is possible that there can be certain cases where the number can't be represented by ratio, and they are called these irrational numbers, like this √2, √3, pi, e, the base of natural logarithm, they are all irrational numbers. What is pi? Can you say? I hope you remember, pi is definitely not 22 upon 7. This is not correct. Pi equal to 3.14, etc. That is also not correct. What is the definition of pi? Pi is the ratio of perimeter of a circle to its diameter. Perimeter of a circle P by diameter is equal to pi, leading to perimeter is equal to pi into d. So, pi is always the ratio of the perimeter to diameter of a circle. This quantity was measured to be constant long back, hundreds of years back. People working on geometry measured this, and they are surprised to see that this particular ratio always remains constant for any circle of any diameter size, and that was given the name pi. So, pi is one of the irrational numbers. While rational numbers can have integers and fraction kind of representation, irrational numbers definitely can't have any such representation, rather they are commonly represented by their own. This 22 upon 7 or 3.14, whatever may be the number of digits you want to keep on adding, that will only give you an approximate value of the pi. It is a never ending series, and 22.7 is never correct, and 3.14159 dot 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 dot, that will keep on continue for infinite length. The same for this e or any other, like what is root 2, 1.414 dot dot dot, it's an infinite series. So, these are all irrational numbers. If we find an end of the series, we can always represent them to a rational form. Like suppose you are dealing with a number of 2.73645121112, something like this. So, it is a very long number. Can we have a fractional representation of this? It is very easy. Just check how many number of digits we have after the decimal point. Here we have 1, 2, 3, 4, 5, 6, 7, 8. Let me remove the decimal point itself. We had 2 before that, and now as there are 8 numbers, 8 digits after the decimal point. So, in the denominator put 8 zeros, 1, 2, 3, 4, 5, 6, 7, 8, and it is a ratio. Now we are giving the same value. You can simplify it whatever you want, and you are having a perfectly rational numbers. And so, rational numbers and irrational number together give us the real numbers, which can take any kind of value. Now, the numbers can have 4 kinds of properties. One is closure. Closure refers to if the result of an operation belong to the same number set as the operand, then we said them the number set is closed. Cumulative a plus b, that is equal to b plus a, that is if we change the order of the numbers, but the final result does not change, then we call it cumulative. Then associative, like the example shown here, if we change the grouping of the numbers without change, that does not change the result. And finally, distributive, if the number is multiplied with the sum of 2 other numbers, then the first number can be distributed to both the numbers and multiplied by each number separately, and then added without changing the result, like shown here. A into b plus c is equal to ab plus ac. Now, it may seem a very obvious operation, but may not be possible for all kinds of numbers. Like for integers, the closure is okay. There are 4 common operations that we do: addition, subtraction, multiplication and division. With addition, subtraction and multiplication, this is okay, but for division you may not always be in the same set. Of course, b is a non-zero quantity, but despite that you may not reach the same data set. Like it may become the result of this one can correspond to a different data set or different set, I should say. Cumulative is not true for subtraction and division, but true for addition and multiplication, because a minus b and b minus a have different meaning. Similarly, a by b and b by a are not equal to each other. Associativeness is also not valid for subtraction and division because of the same reason, and distributive term is valid for addition and subtraction. Of course, they are not applicable for multiplication and division. Look at what we have with rational numbers. For rational numbers, it is just the extension of what we have for integers. If we are talking about rational numbers, then we are going to get a rational data set also after division. But in case of integer, suppose your a equal to 2 and b equal to 5, then your a by b is not going to give you an integer. It is not an integer, you are going to end up with 0.4 or maybe just this fraction, this ratio. Therefore, the data set does not hold. That means this particular condition may be true sometimes, but generally not. But in rational case, the fractions are also included, integers and fractions both are included in rational case. So, the data set can be closed for any kind of operation. However, cumulative and associativeness does not hold for subtraction and division as well. Now, we go to irrational numbers. Irrational numbers, none of the mathematical operation lead to the closure of the data set, because their operation may lead to a rational number itself or maybe something else. Cumulative and associative properties again does not hold for subtraction and division. So, these are certain properties of numbers. Now, how we represent the number commonly? This is the most scientific way of representing any general number, where we clearly have two parts. One, this particular part is called the mantissa, this particular portion is called the exponent. In scientific notation, we always have a 0 before the decimal point, then the decimal point itself, and then whatever digits we have, and these digits are referred to the mantissa. This is the decimal point, and we always have a leading 0, and there may be a sign of the mantissa. It can be negative or positive. For positive numbers, often the sign is ignored, but for negative numbers, of course, we have to put. And then we have this multiplication sign, and then 2 to the power minus 3. This minus 3, minus is the sign and 3 is the exponent, and this 10 is called the base, or quite often it is also called radix of the number. 10 base refers to the decimal number system, but note that is not the only possible number system that we have. We can have infinite number of data sets, but these 4 generally are the most common one. Decimal refers to the base of 10, that means there are 10 possible digits starting from 0 up to 9. But we can also have the binary data set where we have just 2 digits 0 and 1. We can have the octal data set where we have 8 digits 0 to 7, and we can also have the hexadecimal data set starting from 0 to 9, and then A, B, C, D, E, F. Here this A corresponds to 10 in decimal, B corresponds to 11 in decimal, and this way we shall shortly be seeing their correspondence. So, decimal is only one of several possible number base that we can have, but still we generally talk in terms of decimal always, because that is the most common kind of number base that we deal with in our day to day life. Just see how we can represent, like if we are using 1 bit, if we stick to the binary notation, then we can in 1 bit we can just write 0 or 1, because these are the 2 digits. Like if you are using decimal, then any digit out of this 10 0 to 9 can go to 1 bit. Then let us just ignore this particular side, just there are 4 bits, then how many you can have, how many numbers you can represent? You can represent, there are 4 digits you can put. So, these two 9999, these are all you can get. Or if you are talking about binary, then the smallest you can have this, the largest you can have this. If you are talking about octal, this is the smallest you can get, and this is the largest you can get. So, this way we can decide what is the maximum number that we can store in 1 nibble or 1 byte or 1 word or 1 keyword, which refers to 64 bit. But all the bits does not have the same weightage. Once you are storing the numbers in bit, like here we are having 1 byte. So, there are 8 bits, each of the bits are housing one number. It is shown in the binary system. This is the one which is having the largest weightage. If we generally start from the right hand side and their weightage is said to be 0, then 1, and moving this way, the leftmost one is having a weightage of 7. So, the one having an exponent of 0 like this is called the least significant bit, LSB, or least significant bit, whereas the one on the leftmost side which is having the largest exponent or largest weightage, that is called the most significant bit, MSB, most significant bit. LSB refers to least significant bit, MSB refers to most significant bit. That is called the most significant because that influences the final value of this number the most, whereas LSB is the one which influences the least. That is why these names are given. Let us try to see how we can convert across these different number systems. Any common number can be represented, or their decimal equivalent can be represented in a form like this. Say we have a number NB in any base system b, then we generally have a summation of this particular form. Like let us say we start with a decimal case. We have a number say arbitrary 524.1 and we use this subscript 10 to denote that this is something with decimal base. If we in normal operations we do not have to use this because we are always talking about decimal base, but when you are talking about different kinds of bases, then we have to talk about this base. Then how to get the value of this? Now the one which is immediately below the decimal point, this one, there should be given 0, this given 1, this given 2, whereas the one on the other side of the decimal point, that should be given -1. If anything appearing after that, -2, -3, similarly on the other side it will continue as 3, 4, this way. So we have to get the value, we have 5 into base, that is 10 to the power 2 plus 2 into 10 to the power 1 plus 4 into 10 to the power 0 plus 1 into 10 to the power -1, we definitely will return the same value. It may seem very obvious to you, but why you are doing this, that will be coming very shortly. Let us take another example. Let us say we have taken a very long number. Now how to write this in this particular form or in this particular form? So this is the least significant, or which is the least significant bit here? The one appearing the rightmost is the least significant, the leftmost is the most significant. Why? Because of the weightage that we assign. How to assign the weightage? Look at the one immediately on the left of the decimal point. Here we have this 1. So this is having a weightage of 0, next one having weightage of 1, next one having weightage of 2, and this continues this way. Whereas on the other side of the decimal point we pick up -1, then -2, this way. So if we write this, what is the weightage for the most significant bit here? 1, 2, 3, 4, 5, 6. So it will be 7 into 10 to the power 6 plus 6 into 10 to the power 5 plus 5 into 10 to the power 4 plus 4 into 10 to the power 3 plus 3 into 10 to the power 2 plus 2 into 10 to the power 1 plus 1 into 10 to the power 0 plus 1 into 10 to the power -1 plus 2 into 10 to the power -2 plus 3 into 10 to the power -3 plus 4 into 10 to the power -4 plus 5 into 10 to the power -5. So this way we can expand any number in this summation form. Now look at a number of some other digits, other base I should say. Let us take one binary number. We are taking 1101.1. We know we can have only 0 and 1. Then how to get their decimal equivalent? This is the one with 0, the most significant one having weightage of 3. So we are having 1 into, what is the base here? It is binary, base is 2. So 1 into 2 to the power 3 plus 1 into 2 to the power 2 plus 0 into 2 to the power 1 plus 1 into 2 to the power 0 plus 1 into 2 to the power -1. So get their values, this is 8 plus 4 plus 0 plus 1 plus 0.5, that is 13.5 in decimal base 10. That is how we can convert a binary number to its decimal equivalent. Let us try the same with an octal number. Let us say we have 375.3 octal base. So what it will be? We now know that we have 0, 1 and 2, the most significant bit is having weightage of 2. So we have 3 into the base, it is octal. So it is 8 to the power 2 plus 7 into 8 to the power 1 plus 5 into 8 to the power 0 plus 3 into 8 to the power -1, and if we calculate this, you are going to get something. Actually I have noted down the result for this because I do not have a calculator. The result for this calculation is going to be 253.375 in 10 decimal base. Let us do one example with the hexadecimal case. For hexadecimal case, have a D 8 B 0.2 base 16. So, what is the weightage of the most significant bit? This is having a weightage of 2 here. So, we have d into what is the base? It is hexadecimal, base is 16, 16 to the power 2 plus 8 into 16 to the power 1 plus b into 16 to the power 0 plus 2 into 16 to the power minus 1. So, we can calculate the values, but wait, there is one problem. Here d and b are appearing, which never appeared for binary or octal. So, we have to refer to the chart that is on the left. A refers to 10 in decimal, similarly b refers to 11 and d refers to 13. So, replace this d with 13 and replace the b with its decimal equivalent, which is 11. Now, you do the calculation, you are going to get 3467.125 in hexadecimal case. So, you can clearly see as the base of the number, using this particular summation notation, we can convert a number from any base to decimal. We are talking about decimal one and one side always, because that is the most common one that you use in daily life. Another thing that you can see, like in this example, it is a very large decimal number, but quite smaller hexadecimal representation, which is having a higher base, whereas this small decimal number is having a much larger or quite wider binary representation, because we need more number of digits to represent this. Let us quickly try the other one, converting a decimal number to something with a different base. Let us take a random, let us take a, we take a number, randomly generated number 713, which is having a base of 10, and we want to convert it to its binary equivalent. How can we do this? The idea is divide it by 2, divide it by the base of the system on to which you want to convert it. You are originally having a decimal one, you want to convert it to binary, that is why you are dividing by 2. If we want to convert it to octal, we shall be dividing by 8. So, if we divide it by 2, then what we are going to get? We are going to get 3, then 5, 6, but what is left out? That is 1. So, let us note down the 1, divide it once more. So, we are going to get 1, 7, 8, what is left out? It is an even number, nothing left out. So, 0, write the 0 to the left of this one, then divide by 2. So, we are going to get 8 and 9, nothing left out, again 0. So, write 2, divide by 2 again, keep on dividing till you get a 0. So, if you divide 89, 1, 2, 3 step we have done, you divide by 89, you are going to get 44, 1 left out, divide 44 by 2, you are going to get 22 and nothing left out as remainder, divide 22 by 2, getting 11, again nothing left out, 11 by 2, we are going to get 5, now we are having 1 as remainder, divide 5 by 2, you are going to get 2 and 1 in the remainder, divide by 2, you are going to get 1 and nothing left, and now you divide this 1 by 2, you are going to get a 0 and a 1 as the remainder, and what you have got, this is your corresponding binary equivalent, that is 713 in decimal is equivalent to 1011001001 in decimal, in binary. We can get anything else also in the same format. Let us see if we want to get the hexadecimal equivalent for this. So, 713 we divide by 16. If we divide by 16, then what we are going to get? We are going to have a 4 and another 4 here, left out is 9. Divide 44 with 16. So, we are having a 2 and 12 left out here. Now, 12 we can't put, because in hexadecimal there is system, there is nothing 12, but this 12 actually corresponds to this C. So, let us write C, and now divide this 16 again, having a 0, having a 2. So, this 2C9 in 16 hexadecimal system is equivalent to that 713 in binary decimal system. This way we can convert a number in decimal system to a number of any other base. But one advantage we get is once we have the binary equivalent, we actually do not have to calculate octal or hexadecimal equivalent separately, rather we can do it directly. Because look at this, the base for binary system is 2. What is the base for octal system? That is 8, that means 2 cube. What is the base for hexadecimal system? 16, which is 2 to the power 4. We can take the advantage of this one. Like the binary equivalent that we already had, let us divide this number, or I should not say divide, let us write this number by separating the digits in groups of 3 starting from the leftmost. So, in the leftmost we have 1 0 0, then we have 1 0 0, then we have 1 1 0, and then there is only 1 left out. So, but we need to have 3 digits in each group. So, put leading zeros. We know that putting a leading zeros will not alter the value. So, we have divided it is the same binary number, but we have written by keeping a space after every third digit. And now look at them and just try to find out these are the binary numbers for each of these groups. Try to find out the corresponding octal equivalent using the table. 0 0 1 is this, corresponding octal equivalent is 1. So, write 1. 0 1 1 octal equivalent is 3, write 3. 0 0 1 octal equivalent is 1 and it is also 1, and now the octal equivalent for this entire system will be this 1311 base 8. If we want to do it in hexadecimal system, instead of in 3, make groups. I think you can guess. Write the binary number such that there are groups, each group comprising 4 digits. So, we can write 1 0 0 1, then we have 0 0 1 1, then we have 0 1 and no digits. So, let us put 2 zeros before this. So, the same binary number we have written such that there are 3 groups each comprising of 4 digits, and now try to find out the hexadecimal equivalent to each of them. For 0 0 1 0, 0 0 1 0, let me erase the earlier ones. So, 0 0 1 0 is this, its hexadecimal equivalent is 2. So, it is 2. 1 1 0 0, 1 1 0 0, sorry 1 1 0 0 hexadecimal equivalent is C, this is C, and 1 0 0 1, 1 0 0 1 hexadecimal equivalent is 9. So, write 9 and we get 2C9 as the hexadecimal equivalent. Just compare with the previous case, this is what we have got already. These things are called octal or hexadecimal formatted binary, that is a binary number written in a format which allows straightforward conversion to octal or hexadecimal cases. So, this way we can convert any decimal digits to other number bases or any other number base to decimals, and not only numbers, rather any kind of symbols that are available to computers are generally given some kind of numbers following any number system. This is the ASCII character set, there are a few other character set available, but this is the most common one. Here you can see some very common things like this, say capital A has been given a decimal number of 65, small a has been given something of 97, hexadecimal or octal are corresponding representations only, or some abrupt symbol, say this equal to, that is given a symbol of or number of 61. So, if we want to give this equal to symbol to computer, it will read it as 61, ASCII character 61, and then using this number we can do whatever we want. This is just an example of doing this. But final question that we have here, we know all computers or any digital device use binary despite having other number base available. Why it can't use decimal? Because that is the most common one that we use in our day to day life. Why it can't use octal or hexadecimal, which or any other number system? That is because binary provides a distinct advantage. How many digits it has? Only 2, one is 0, other is 1. Now, just relate that to our real life. 0 means what? Absence of something. 1 means the presence of something. That means 0 can be something like an on, I should say 0 can be absence of something, means something like an off. 1 means the presence of the same quantity, that is on, and that is the precise idea. That is why you use binary, because our digital devices are operated by some current, some electricity. And now how we can make the computer understand some decimal digit? it will be much easier for it to make us make understand the octal digit, sorry, the binary digit. You can think about, say, we have a switch kind of representation. So, if we want to make it understand 0, we shall be opening the switch, thereby no current is flowing. If we want to make it understand 1, we shall be closing the switch, thereby allowing the current to flow. So, just by on or off position on the switch, you can make it understand this 0 or 1, and that is why interfacing becomes very easy. We can easily make the computer understand what we want to give as input. Just compare it with decimal. Here we have, in binary we have only two logics, one is off, other is on, but in decimal how many we have? Let us say our computer is having a total 10 volt system. So, our on will refer to 10 volt, off will refer to 0, or when the circuit is open, there is 0 volt, it will read as 0. When it is closed, whatever voltage it is giving, it is reading as, it will read as 1. But if we want to make it understand decimal, then what it will do? Then this 10 volt, this entire 10 volt span needs to be separated into small components, like when it is 0, it will read as 0. Now, when the value is something like between 0 to 1 volt, then it may read it as 1. When it is between 1 to 2 volt, it will read as 2. This way there are 10 different logics we have to get, which are very cumbersome, very difficult to deal with. So, that is the main reason we go for binary system in any digital instruments. And this is the way you can visualize. One is the on situation, other is the off situation. So, if we want to give input for a single bit, we shall be providing one on to represent 1 or an off to represent 0, which can be very easily done. We shall be seeing that in the next lecture how that is done. If we want to give input for 2 bits, then we can have two simultaneous switch. When both the switches are on, your input will be 1 1. When first one is on, second one is off, it is input is 1 0. First one is off, second one is on, it is 0 1, and last case both are off, so 0 0. So, very easily you can give such inputs. You just need two logics for each of these switches, and then you can make any combination of that. But if we want to have the same using decimal or any other operation system, other number system, we need to have lots and lots more logics. Like for decimal we need 10 logics for a single switch, and now 10 square number of combinations for two such switch, and that will exponentially keep on increasing, which is not required in binary system. Some binary logic gates, I thought about discussing it today, but I am skipping it today in the next lecture as the time is over. So, in the next lecture I shall be starting from this point onwards. So, what we have learned today? We have learned about the analog and digital signals. We have discussed in detail the advantages of digitalization or digitization. We have discussed briefly about the method of digitization. Then we talked about bit, byte and word, which are the fundamental units. Then the number systems and conversion from one system to another system that we have discussed about, and we have discussed about the advantage of the binary system. My plan was to discuss about logic gates, but I shall be discussing in the next class, because I do not want to extend it anymore. So, the lecture will be continued. Tomorrow we shall be starting with the logic gates, and then we shall be seeing how we can combine different logic gates to give much longer input, and then some fundamental components of electronic circuitry about how to achieve these steps of digitalization, thereby proceeding further to analog to digital or digital to analog conversions. So, that is it for the day. Thanks for your attention. Hopefully, you have enjoyed it. If you have any query, please write to me immediately and wait for the next lecture. Thank you.